Early flight attempts often ended in catastrophe, not from a lack of power, but from an incomplete understanding of how air itself interacts with moving bodies. The Wright brothers, for instance, spent years in iterative glider design, meticulously observing camber and dihedral effects, before successfully achieving controlled, sustained flight. Their challenge was not merely to generate lift, but to understand its nuanced relationship with drag and stability, a complex dance engineers continue to refine. At its core, aircraft design balances four fundamental forces: lift, weight, thrust, and drag. Achieving flight requires lift to overcome weight, and thrust to overcome drag. However, optimizing these forces simultaneously often presents conflicting requirements. A wing optimized for maximum lift at low speeds might generate prohibitive drag at high speeds, illustrating an immediate design trade-off. The primary mechanism for lift generation is the airfoil. Engineers select specific airfoil profiles based on the aircraft's intended speed regime and payload. A thicker, more cambered airfoil, like the NACA 2412, excels at producing high lift coefficients at lower speeds, ideal for general aviation. Conversely, thinner, more symmetric airfoils are preferred for supersonic aircraft, minimizing wave drag. The pressure differential created by airflow over and under the wing, combined with the downward deflection of air, directly produces the upward force, governed by principles like Bernoulli's equation ρv²/2 plus p = constant, and Newton's third law. Minimizing drag is equally critical. Total drag comprises parasitic drag and induced drag. Parasitic drag includes form drag, skin friction drag, and interference drag. Form drag is reduced by streamlining the fuselage and nacelles, ensuring smooth transitions and minimal frontal area. The iconic teardrop shape of many aircraft fuselages is a direct result of extensive aerodynamic optimization to minimize pressure drag. Skin friction drag depends on the surface area and the smoothness of the aircraft's exterior. Engineers meticulously design the outer mold line, specifying finishes and avoiding protrusions to maintain laminar flow for as long as possible over surfaces. Rivet lines and panel gaps, seemingly minor, significantly contribute to parasitic drag, leading to the development of flush riveting and composite materials to achieve smoother surfaces. Induced drag, intrinsically linked to lift generation, arises from wingtip vortices. As air flows from the high-pressure underside to the low-pressure upper side at the wingtips, it creates swirling vortices. These vortices consume energy and tilt the lift vector rearward, adding a drag component. Engineers address induced drag through increased wingspan, elliptical wing plans, or the integration of winglets, which effectively increase the aspect ratio without a corresponding increase in bending moment at the wing root. Control surfaces, ailerons, elevators, and rudders manipulate the aircraft's attitude. Ailerons, located on the trailing edge of the wings, induce roll by differentially changing lift on each wing. Elevators on the horizontal stabilizer control pitch by altering the lift generated by the tailplane. The rudder on the vertical stabilizer controls yaw. The size, shape, and placement of these surfaces are precisely calculated to provide adequate control authority across the aircraft's flight envelope, often requiring careful balancing with stability requirements. For takeoff and landing, high lift devices are deployed. Flaps on the trailing edge and slats or leading edge devices on the leading edge of the wing increase both the wing's camber and effective surface area. This allows the aircraft to generate sufficient lift at lower airspeeds, reducing takeoff and landing distances. However, these devices also significantly increase drag, necessitating careful management during these critical flight phases. High-speed flight introduces compressibility effects. As an aircraft approaches the speed of sound, local airflow can become supersonic even if the aircraft itself is still subsonic. This can create shock waves, leading to a sudden increase in drag, known as wave drag, and flow separation. Swept wings delay the onset of wave drag by effectively reducing the component of airspeed perpendicular to the leading edge. Supercritical airfoils are designed to delay shock wave formation and reduce its strength, optimizing performance in the transonic regime. The interaction between aerodynamics and structural design is a constant negotiation. Aerodynamic forces impose significant loads on the aircraft structure. A lightweight structure is desirable for performance, but it must withstand these loads, including bending moments, shear forces, and torsion. This often leads to compromises. An aerodynamically ideal shape might be structurally impractical or too heavy, forcing engineers to iterate between aerodynamic efficiency and structural integrity. Materials science advancements have directly impacted aerodynamic design. The introduction of aluminum alloys allowed for larger, more complex structures than earlier wood and fabric designs. More recently, composite materials like carbon fiber reinforced polymers offer high strength-to-weight ratios and the ability to mold complex, aerodynamically smooth shapes that are difficult or impossible to achieve with traditional metals, further optimizing both lift and drag characteristics. Computational Fluid Dynamics, or CFD, has revolutionized aerodynamic design. Before CFD, engineers relied heavily on theoretical models and empirical data. Now, complex flow fields can be simulated digitally, allowing for rapid iteration and optimization of airfoils, wing-body junctions, and control surfaces. This virtual testing reduces the need for expensive and time-consuming physical prototypes, though it does not eliminate them. Wind tunnel testing remains indispensable. While CFD provides valuable insights, physical validation in a controlled environment is crucial. Wind tunnels allow engineers to directly measure lift, drag, and moments on scaled models, observing flow patterns using smoke or tufts. These tests calibrate and validate CFD models, revealing real-world effects that simulations might miss, such as unexpected flow separation or turbulent boundary layer behavior. Every aspect of an aircraft's design involves engineering trade-offs. Maximizing speed often means sacrificing low-speed performance. Achieving high fuel efficiency might compromise maneuverability. The selection of wing sweep, airfoil thickness, and control surface sizing all represent deliberate choices based on the intended mission profile. These decisions weigh factors like operational cost, passenger comfort, safety regulations, and manufacturing feasibility. Ultimately, the design of an airplane is an intricate optimization problem, where the application of fundamental aerodynamic principles is continually balanced against material constraints, manufacturing capabilities, and operational demands. This iterative process, refined over a century of flight, continues to push the boundaries of what is aerodynamically possible.